Have you ever stopped to think about how we control something as wild and powerful as electricity? The secret, well, it's probably not what you're thinking. It isn't about perfection or purity. It's actually all about the power of imperfection. So let's dive into how we use these carefully engineered flaws to tame one of the most powerful forces in nature.
I mean, just look at this. Electricity is raw, untamed power. We see it in lightning, and right here, it's arcing uncontrollably in a lab. This stuff powers our entire world, right down to the device you're watching this on. So the big question is, how did we go from this chaotic, wild energy to the incredibly precise control we rely on every single second of our lives?
Well, the answer lies in two completely different worlds, at two totally opposite scales. On one hand, you've got the massive country-spanning power grid, and on the other, you have the impossibly small world inside a microchip.
To put that first scale into perspective, we're talking about high-voltage transmission lines that are humming with 400,000 volts. That's just an immense, almost unimaginable amount of energy.
And then you have to completely flip your thinking. We jump to the other extreme, the world of semiconductors, where the tiny components that control all that electricity are measured in nanometers, a scale that's thousands of times smaller than a single human hair.
Let's start with the big stuff, the electrical giants. How in the world do you contain hundreds of thousands of volts and push it across an entire country without it just, leaping out into the air? The engineering challenge here is just staggering.
To pull it off, for starters, we build these absolutely colossal towers. They're basically the skeleton of our modern world, and they're designed to do one thing: hold incredibly heavy, highly charged conductors way up high, far away from the ground.
These towers then connect into these incredibly complex substations. You can think of these as the nerve centers of the grid. It's where all that electricity gets rerouted and where voltages get cranked up or down for the journey.
And remember, all of this power originates in these massive generators. This is where mechanical energy gets converted into the electricity that's going to travel hundreds of miles through those very conductors.
Now, the real unsung hero that makes all of this work is the humble insulator. We're talking about materials like glass and porcelain. Their entire job is to do one thing and one thing only: stop electricity dead in its tracks. They are the cage for the beast, preventing all that voltage from jumping from the wire to the tower and into the ground.
Okay, so on the macro scale, the whole name of the game is to stop electricity from going where we don't want it. But now, get ready for a total switch. We're going to pivot to the microscopic world, where the goal is the complete opposite. Here, we don't want to stop electricity. We want to control its flow with unbelievable precision. And right away, we run into this fascinating paradox. The foundation of all modern electronics is silicon. But here's the kicker. Perfectly pure silicon is actually a terrible conductor. On its own, it's pretty much useless for what we need it to do. So, what do? We mess it up. On purpose. The process is called doping. We intentionally add these tiny, carefully measured amounts of other elements, impurities, into the pure silicon crystal, and that completely changes how it behaves with electricity.
This breaks down the two main ways we do it. On one side, we can add an element like boron to create what's called p-type, or positive-type silicon. A great way to think about this is that it creates holes, like a bunch of empty parking spots that electrons are just dying to jump into. On the other side, we can add phosphorus to create n-type silicon. This does the opposite. It's like adding a bunch of extra cars to the traffic flow, providing a surplus of free electrons ready to move.
And the way we do this is just mind-blowing. It's a technique called ion implantation. You can picture it like a subatomic shotgun, firing individual atoms of that impurity right into the silicon wafer, placing them exactly where they need to go. We're talking about control at the atomic level. It's incredible.
So, now we have these two completely different worlds, right? One using materials to stop electricity, the other using materials to make it flow just right. So, what's the hidden connection? This is the real aha moment, and it's just fantastic. So here it is, the secret to controlling electricity at both the colossal scale and the microscopic scale is engineered imperfection. In both worlds, we take these pure, almost perfect materials, and we intentionally make them flawed to achieve control.
And this just lays it out so perfectly. In high-voltage engineering, insulators like glass, well, they aren't perfectly structured crystals. It's their mixed-up, impure nature that actually stops the current. Then, in semiconductors, we add impurities like boron specifically to create and direct a current. You see, in both cases, perfection is actually the enemy of control. Our mastery comes from deliberately introducing these flaws.
Okay, so now let's see how these engineered imperfections actually work together, connecting that massive power grid all the way down to the tiny gadget that might be in your hand right now.
When you put a piece of our P-type silicon right next to a piece of N-type silicon, something truly amazing happens right at that boundary. They form something called a P-N junction. And this junction acts like a perfect one-way valve, or a gate, for electricity. It lets the current flow easily in one direction, but it blocks it almost completely in the other. And this simple one-way gate, a gate that was born from combining two different kinds of imperfections, is the key to everything. I mean, everything is the fundamental building block for the transistor, which is the microscopic switch that powers every single computer, phone, and modern electronic device on the planet.
So there you have it. We master electricity by using impure insulators to contain its brute force on the grid, delivering it safely to our homes. And then, inside those homes, our devices, filled with impure silicon, use that power to think, communicate, and compute. It's a really beautiful symmetry when you think about it.
So, our entire digital world is built on a foundation of engineered imperfection. It makes you wonder, doesn't it? As we look to the future, what's the next great breakthrough that will come not from seeking perfection, but from finding the incredible power that's hidden inside the flaws?